Thanks, Kayla. Hi, everybody. I will admit I will not get us back on time. So today, once again, I'm here talking on behalf of a lot of smart people. I just happen to be the talking head for the group, and we're looking at nutrient transport down in the Leamington area. So Leamington's known as a hotspot for nutrient loading into Lake Erie. And really the objective of this study, which was dreamed up by Helen Zhang at the MECP, was to try and identify the role of groundwater and groundwater surface water interactions with the nutrient migration from the greenhouse landscape and the agricultural landscapes down in the Leamington area. So we'll acknowledge the contributors of data and insight to the project. The Essex Region Conservation Authority provided us flow data, water quality data. We're still using the Geological Survey of Canada's geological model that was put together in the 2018 to 2020 timeframe. That was very useful for this project, and Environment and Climate Change Canada provided quite a bit of flow data for model calibration. And as I really mentioned earlier, we're trying to characterize nutrient migration pathways down in an area with a lot of unique land uses. So there's a lot of greenhouse activity in Leamington. Greenhouses discharge pretty nutrient-rich water into receiving ponds, and the question remains, where does that water transport? What are the transport pathways from these ponds, these receptor ponds, out into the lakes and the surface water features? Ultimately, we hope some of the results from this research can go towards supporting beneficial management practices and new policies towards greenhouse wastewater management. So our model domain, and when I'm talking about model, this is a fully integrated groundwater surface water model that we're using here. So we're fully coupling subsurface flow processes with overland flow processes with in-channel flow processes. It's 460 square kilometers, which is a fairly large domain, so we're not able to drill down in anybody's backyard with a model of this scale. But in terms of what these types of models are being used for now, this is a very manageable domain area. The model extends out into Lake Erie, so we've got a 1 kilometer buffer extending out into the lake, and that allows us to capture the groundwater fluxes from the terrestrial portion of the domain out into the lake bed. And at certain times of the year, vice versa, water moving from the lake bed into the terrestrial groundwater system. The domain also captures the surface water catchment area flowing north up into Lake St. Clair, as well as down into Lake Erie. And the green boxes are the greenhouse footprints. So we digitized, I think, 230 greenhouses and embedded those greenhouse footprints into the model. So this is a pretty big area, and there are a lot of greenhouses here. It's pretty impressive, actually. So if you're wondering where your cucumbers and peppers are coming from this time of the year, if they have a Made in Ontario sticker, it's likely from one of these green boxes. The finite element mesh, so the model we use actually projects the mesh down through the hydrostratigraphic layers. This is just a plan view perspective, and we put more detail into the mesh around the surface water features and areas of interest. So you can see the unstructured nature of this plan view mesh. In general, along the streams and rivers, we're carrying 250 meter resolution. We extend that resolution up to from 250 meters to 500 meters in the more distal areas from surface water. In total, the model has about 225,000 computational nodes, which isn't huge for this type of model. Superficial geology, this isn't a map we're actually using in the model, but to give us a perspective of what the superficial geology looks like, really we can think of that superficial geology as one of the main drivers of the ability of groundwater to interact with surface water in this area. We've got glaciolacustran sands and gravels, and a lot of lower permeability till and clay plains. We've also got organic deposits out into Point Peely. So I mentioned we're using the GSC's hydrostratigraphic model. We're primarily interested in this model for the superficial geology representation because, again, we're dealing with groundwater surface water interactions here. The deeper flow system wasn't as interesting to us. So we focused on really the overburden layers, and we took the model domain down to the top bedrock surface. We did benchmark the GSC's hydrostratigraphic model against new borehole data that was obtained since that GSC model was constructed. And the benchmark data compared very well to the model. So we didn't actually end up having to do any updates to the hydrostratigraphic model in order to get a good handle on the superficial hydrostratigraphy. And then on top of the superficial geology, we've got spatially distributed soils that we pulled from the Ag Canada database. Calibration targets. The unique thing about the groundwater surface water modeling is that we can use both groundwater levels and surface water flows and remote sensing data products to try and calibrate and validate these models. The main surface water gauge point here was the Ruscombe River site flowing north up into Lake St. Clair. Environment Canada has a pretty consistent record of flows at that location. We've got 3 PGMN wells in the domain, and then we've got some of the Conservation Authority's flow stations as well. So we put all these gauge points into the model. We use those for calibration and validation targets. There's transient reproduction of flows at the Ruscombe River site. Over a 7-year time interval, statistics are good, so we're capturing the peaks and valleys and flows. It's a pretty flashy hydrologic system, so the system responds really quickly to climatological events, which makes sense. It's primarily a clay plain, a lot of till, so it's inherently going to be flashy with kind of spiky hydrographs. The model does a good job of capturing that spiky behavior. The overall flow biases are good as well. So flow system was well resolved in the model. We also so we're moving towards using remote sensing data to validate these models. So when we're dealing with big domains, we often don't have gauging data available to fully capture the spatial distribution within the model performance. So we're looking at remote sensing to assess surface water expression. So we can use surface water expression as kind of an analogy for groundwater levels. So this is a remote sensing data product overlain with the hydrogeosphere model outputs. And really, I could have renamed this slide The Life of a Hydrologic Modeler from Despair through to Euphoria, because when you look at this picture out of the model and you compare it to the real world, you think, oh my gosh, we've turned Point Pelee into a swamp. And you think, okay, why should that happen? Because this model is fairly well constrained by boundary conditions. We've got time-varying boundary conditions in the lake that should really drive the nearshore surface water levels. But Point Pelee is largely inundated. Well, it turns out the model's right here, with the exception that we didn't put in groundwater extraction and dewatering. So there's a massive amount of dewatering that's undergoing in Point Pelee to support the intensive agriculture. So that area that's inundated as a swamp in the model, that really divides Point Pelee from the larger shoreline, that's effectively dewatered to support the agriculture. Now, when we're thinking about nutrient sources, and the objective of this project was to try and sort out what the role of the greenhouses is, looking at this slide, the next thing I think we might want to consider is what's the role of the dewatering within the Point Pelee area on the water quality in that area of Lake Erie, because this is pretty intensive agriculture, it's very valuable land, and they're growing high-value crops, so they're not afraid to put on nutrients to get the maximum production out of the landscape. So interesting kind of side note from this whole project, and very interesting because when we looked into the source of that flooding, we realized, wait a minute, the model's right. We didn't do anything to screw it up as we constructed it. So, in the end, we were happy with this, but when you first looked at it, it's like, oh man, something's gone off the rails. Groundwater calibration, so I mentioned we've got the 3 PGMN wells. Overall, the model kind of overestimates the groundwater levels, not to be expected. We also don't fully capture the annual variability in heads that we see in the monitoring data. Again, maybe not to be expected. It is a fairly large model. The local heterogeneities, not entirely resolved in the hydrostratigraphic data that we've incorporated, but all in all, not bad. So we ran the model then, and we won't get into the climatological data, but we ran the model for a 7-year transient historic simulation period, and we teased out the water balance into the individual major components. So we've got liquid water forcing, which is essentially rainfall plus snow melt. Then we've got evaporation and transpiration, which is the uptake from the vegetation. Direct groundwater discharge into Lake Erie. So this is a unique aspect of a groundwater surface water model that we're able to capture, is that direct groundwater flow from the terrestrial portion of the domain into the lake. We've got the groundwater discharge to channels, and then we've got direct surface water outflow into either Lake St. Clair or Lake Erie. And what we can see from this is, in general, and this aligns with what we know about clay-till type domains where there isn't a whole lot of groundwater surface water interaction. There's not a lot of groundwater contributing to the surface water system, so base flows are generally low. It's a low base flow index area. That's known from other studies as well. The direct groundwater discharge to Lake Erie, also a relatively small component of the water balance. And just looking at this, it kind of frames what we will expect now when we look at the nutrient transport and the loads coming off the greenhouses into the lake through the groundwater system. So the other thing that we have to take into account is that the lake levels oscillate kind of opposite of the terrestrial water levels. So we get this kind of switching of hydraulic gradients over the course of an annual cycle in these lake areas, where we can move from a recharge zone to a discharge zone along the shoreline, depending on what the lake elevations are relative to the terrestrial kind of water table position. And this is an important part of kind of cycling in shoreline environments. So it's captured in the model and comes into play when we look at some subsequent results. So I mentioned we're looking at mass loading. And when you're dealing with a domain that's on the order of 460 square kilometers, for modelers, the advection dispersion equation is usually out. So when you're looking at transport in numerical models, grid discretization is kind of a constraining factor. So we're more and more interested now in looking at large-scale nutrient transport and contaminant transport, but we have to think about new numerical methods. So we're now employing what's called a hydraulic mixing cell. You can essentially think of it as advective transport in a flow model. So we're not dealing with dispersion, we're not dealing with diffusion. It's a lot less friendly to the solver, so the numerical, the sparse matrix solver is a lot easier to chew through a hydraulic mixing cell type problem than it would be a advection dispersion equation type problem. So anyway, we're using this kind of, you can think of it as mass conservative particle tracking. And we're using this to track the loads coming off of the individual greenhouses. So we discretized the domain such that we had these 230 greenhouse footprints kind of represented as sources in the model. This is just an individual greenhouse, but we did this essentially for all 230 greenhouses, thereabouts. And we're looking at the transport pathway from water, essentially tagged water coming off of that greenhouse site through into the surface water system and then out into the lake. And this is essentially a classic cumulative effects type of analysis. We ended up doing it, like I say, for all 230 greenhouses. So we've got these footprints, and we can look at the flows now. So this Q value, 4.89 e to the negative 5 cubic meters per second, that's the volume of water being discharged through the Lake Erie shoreline from water sourced from greenhouses. So this is a very, very low percentage of the region's annual water balance. And further highlights that when we're looking at this region as a nutrient hotspot, it's not necessarily direct groundwater discharge and nutrient migration from the greenhouses, from the wastewater ponds into the lake. There's other transport mechanisms. And if we think back to the role of groundwater discharge on surface water flow and the fact that it's a fairly low base flow type of an environment, it likely points to groundwater not really being a big culprit at all. But we're still doing work to analyze the outputs from this model. So just some concluding remarks, which I pretty much already summarized. Groundwater is not playing a huge role in the direct nutrient loading from the greenhouse effluent into the lake. We haven't fully teased out the answer to how much of a role it's playing on groundwater discharge into streams and then the stream water flowing out into the lakes. It's likely not going to be huge. The model's pretty cool. It can be used for a lot of different applications going forward from now on. And I also think it's really going to be interesting to look at the role of dewatering in that Point Peely area to see what potential role it's playing in the nutrient loading down from that part of the province. So, thanks.